Okay, well, much as I'd like to show you Goldie videos all the time, random images of my dog running through the woods, I need to give you an actual lecture and to draw you in, hopefully, with the content of my lecture and not just cute images of Goldie. So today I want to cover the science basics. A lot of this material we've already covered before, and much of it's going to be a review for those of you who are specialists in scientific areas. But it will be important to see it as a whole and to cover these main issues. So today we're going to look at the carbon cycle and cover the long and short-term carbon cycles. I want to make sure that you fully understand the greenhouse effect and key feedback mechanisms. And then terribly important is understanding the scientific process, the role of peer review and the role of the National Academy of Sciences and groups like the Intergovernmental Panel on Climate Change in providing scientific assessments that help us determine what we can and cannot know about climate change. So our objectives for this week, again, are to explain this carbon cycle, this greenhouse effect, make sure you all really understand what this is, peer review, and these basic feedback mechanisms. The carbon cycle. I need you to actually focus on these chemical formulas and to understand what they mean. Again, this is very basic, but the C, the O, and the H all stand for elements. These are elemental, these are elements that exist in nature and combine with other elements to form molecules. So CO2 is a molecule we call carbon dioxide, formed of the elements carbon and oxygen. The two means there are two oxygens and one carbon. Two is di, so dioxide, carbon dioxide, right? We could call water, H2O, dihydrogen oxide if we wanted to, right? Because there are two hydrogen atoms and one oxygen atom. So together then H2O is water, so we have carbon dioxide and water plus light energy equals C6H12O6, that's glucose, stands in for a variety of different sugars plus oxygen. The 6 balances out this chemical equation. So the number of carbons on one side, 6 carbons, has to balance the number of carbons on the other side, also 6 carbons. There is no gaining or loss in this chemical equation. You have the same number of atoms on one side as you do on the other side. They combine differently to make different molecules. Light energy is important because this is a difficult thing to do, to combine carbon dioxide and water together and transform it into a basic sugar, glucose, and oxygen. So you require energy to go into the system in order to be able to make this transformation. This, again, is the basic equation for photosynthesis, and everybody must memorize this equation. That's going to be on the quiz coming up. I'm going to ask you to write out one of the equations that I'm talking about today. 600 million years ago, before there was this Cambrian explosion of life, the carbon dioxide in the atmosphere was between 6,000 and 7,000 parts per million. So this Cambrian explosion that we can see in the fossil record is on the seafloor, right? We don't have life on land at this point. So these sea creatures then developed and the small bits of life expanded into larger organisms. And this led then to a rise in oxygen with that process of photosynthesis happening with these some microscopic plants and some larger plants in this period. The reverse, if you will, is called burning. So this is when we take that basic a molecule of sugar, C6H12O6, and we add oxygen to it, that's called breathing. We breathe in oxygen from the air. It burns the glucose molecules, the basic sugars in our body, and then we breathe out carbon dioxide, and from that we get energy. So when our breath then has this extra carbon dioxide and this extra water vapor that comes out as a part of that metabolic process of burning that's happening inside our bodies. We need oxygen in order to be able to do this. And when oxygen levels are high enough, animals like us, land animals, can appear. The levels of carbon dioxide in the atmosphere for about all of human existence have been down at around 250 to 260 parts per million. So compared to the 415, 417 we have right now, that's much, much lower. It is a lot lower, by an order of magnitude lower, than what was the case back in the Precambrian period. Now, another way to think about burning is to look at the molecule for methane, CH4. And you add this to oxygen, the result of this kind of burning is also carbon dioxide and water vapor plus energy. In this case, that energy can be in the form of a flame. It actually burns in the sense that we normally talk about burning, in producing heat and light energy that we can make use of by cooking or heating our houses. Many natural processes burn fossil fuels, but we're doing it much faster. And in that process of burning, whether it's methane in this case, or oil or coal, we are changing the atmosphere, slowly raising those carbon dioxide levels. Again, we aren't going to reach this 6 to 7,000 parts per million of carbon dioxide, but we are going to raise it significantly more than that 250 that it had been for most of human existence. So let's understand these short and long-term carbon cycles. Again, this is review. You should be able to have this all clear in your mind. That short-term has to do with renewable fuels. These are cycles that go back and forth within a lifetime or maybe 100 years. That carbon cycle, that carbon store, such as charcoal, for example, when it's burned, it can be recycled then, that carbon in the atmosphere drawn back into woody plants that then grow and can be cut down and produce more charcoal. So in this way, we have a sustainable cycle of reuse. There are lots of cycles in the short term. Again, breathing is one of them. If you watch that video, which I do recommend to you, on the chemical processes of carbon cycles and moose farts, that is all part of the short-term carbon cycle. The long-term carbon cycle then is part of this burning of fossil fuels. This is engaging in a cycle that actually unfolds over millions of years instead of the very short term we've been talking about. So again, we talked with Dr. Smithwick this week. Her work on forests and forest burning and forest fires is part of that short-term carbon cycle, right? Forests naturally burn, they renew, they grow again, they burn. This process is all part of a short-term carbon cycle. And yet, the climate change that we are seeing is changing those cycles. We would normally depend on forest burning and forest renewal to help to moderate the CO2 in the atmosphere. But now this increased amount of burning is actually adding to the problem. So as CO2 rises in the air because of our fossil fuel burning, that greater concentration in the air also works its way into the water. The lecture by Richard Alley that was recorded for you makes a really great example of this, and the fact that that mixing happens at the surface of the oceans rather quickly and takes a long time to get into the deeper oceans. We'll also be talking with oceanographer Ray Najar later on in the semester and be able to dig into the role of the oceans in much more depth in this process. The balance of gases as it changes in the atmosphere then affects the oceans, and one of the processes that the oceans use to deal with this greater amount of carbon dioxide is ocean acidification. So this doesn't mean that the oceans are getting acidic. It means that the amount of carbonic acid is increasing and changing the pH balance of the oceans. This is something of great importance when we're talking about animals like corals and animals that have shells, because it becomes more difficult for them to produce these shells in this changed, more acidic environment. So again, it is the burning of these fossil fuels buried in the ground for millions of years that is exemplary of this long-term carbon cycle. Now, this question of trust is of central importance because, as Ali says when he opens up this chapter, if you just want to believe him, move on to the next chapter, right? We can make an argument from authority. Those of you who are inclined to obey authority should just obey me, that this is real, and move on with your lives. But we're scientists here, we're scholars. We should be skeptical about all of this, and we should want to understand the basic processes because it makes us better communicators of this process to the general public. Now, you look at this graph here, and you find that way back in the end of the 1950s, scientists already started to become concerned about the level of carbon dioxide in the atmosphere. So they set up an observatory in Mauna Loa, on top of Mauna Loa, one of the great peaks in Hawaii. And this, because carbon dioxide is a well-mixed gas, this helps us to understand the levels of carbon dioxide not only in Hawaii, but in fact all over the world. So from this point in the late 50s until the present, we have direct measurement of carbon dioxide. This is not just some theory, this is not some imagination, these are real numbers, this is observed reality. And you can see that back in 1958, the amount of carbon dioxide in the atmosphere was down below 320, so already above what we know as the pre-industrial age from our examination of ice cores, and that it has risen significantly up to the present, now rising above 400 parts per million. So we are getting close to a doubling of the carbon dioxide level that was in the atmosphere in the pre-industrial period. Note also this shift every year up and down and up and down. Again, Richard Alley talked about this briefly, that this has to do with the fact that the northern hemisphere is covered with forests, and that those forests then come alive in the spring and breathe in lots of carbon dioxide, which then they release in the fall as that material decomposes and they stop pulling that carbon dioxide in. So that's why the amount of CO2 in the atmosphere actually dips a little bit in the northern summer and then goes back up in the northern winter. The southern hemisphere does not have that same kind of variation because it is largely water. Now, this observatory led scientists to become alarmed at the rising carbon dioxide. Now, remember what we said before, that this comes about because of the developing consumer society, the increasing use of fossil fuels in the 1950s. Scientists all saw this and were concerned about it, reported it to the president. Back in 1965, President Johnson makes a report to Congress about the concern of rising carbon dioxide levels due to fossil fuels. So this is not some new issue, some new imagination of scientists trying to change our society. This has been around for my entire lifetime. The National Academy of Sciences, then, this very body that Richard Alley talks about, was tasked with the report of reviewing the science. And this is now during the era of Ronald Reagan, who became president in 1980, Republican president, who tasked the National Academy of Sciences with this report. They reported to him in 1983 that the climate was in fact changing. And again, as Richard Alley points out, their basic calculations of what they would expect to see in the future in terms of temperature rise are still the basic calculations that we use today. That science is good, it's been tested and shown to be relatively accurate, although of course there's been a lot of work done since that point. The Intergovernmental Panel on Climate Change is not some international conspiracy. It was started by the United States. We are the ones who pushed for this panel to exist. And in fact, its first report in 1990 resulted in, again, Republican President George H.W. Bush attending the Rio Climate Summit in 1992. 1992, I think that's before any of you were born. In 1992, and promising action. You can look this up. There are video recordings of George W. Bush promising action on climate change. He, in fact, pushed the US Senate to ratify the international treaty which governs the study of climate change throughout the world, what's called the United Nations Framework Convention on Climate Change, with UNFCCC. October 15th, 1992, this is a binding treaty entered into by the United States and ratified by the US Senate under a Republican administration. There have been 5 assessments altogether. The most recent one came out in 2014. There was an interim assessment that talked about the problems of the temperature rise of 2 degrees that came out last year. And then the 6th assessment is due out in 2022. It's terribly important to understand the role of peer review and scientific assessments among scientists in determining what is good and useful science and what is not. So this is not some single scientist doing an experiment on their own in the world. These are scientists, and again, as Ali said, scientists are devoted to arguing and debunking and undercutting one another. They are trying to find the flaws in the data. And this argument back and forth results in these assessments where they don't say this is true or this is false. They say this is extremely likely, this is well known, this is something we have high confidence in, or that we have low confidence in, but could be a problem and is worth study in the future. So this is the way scientists talk about climate change, and the assessments are available for you to see on the web. I strongly encourage you to look at these. This will be important for that final negotiation project that we do in this class. So, what are greenhouse gases? Well, again, the basic science of greenhouse gases goes back to that 19th century. It was Eunice Foote, an American scientist, who first saw this role of carbon dioxide and water vapor in trapping heat, and she became concerned about climate change. It was the 19th century, so she could not publish the paper in her own name. She had a man read it to the national meeting in her stead. It so happens that Penn State has just acquired the papers of Eunice Foote, so you can go into the Penn State archives and you can see her original papers and notes of her experiments. Eunice Foote has only recently been rediscovered for her role in this because John Tyndall, a couple of years later, published the basic science of what we consider to be the basic science of the role of atmospheric gases in the greenhouse effect. And he didn't mention Eunice Foote at all in his paper. So this is what women struggle with, women scientists. It's been a long road. The basic issue here, though, is how gases in the atmosphere trap radiant heat. So what we have to understand here is that without the sun, the Earth would be freezing. The sun is what ultimately provides the heat to the planet Earth. And without the atmosphere, the Earth would only heat up on one side and be very cold on the other side. So the atmosphere is like a blanket around the globe. And when the sun heats up the surface of the Earth, and then that warmth would radiate back into space, it's the atmosphere that traps that. Now, interestingly, as you may know, our atmosphere is made primarily of nitrogen, and then there's quite a bit of oxygen. But these gases do not trap radiation in the way that carbon dioxide does. Again, carbon dioxide, if we talk about 400 parts per million, that's the same as saying that carbon dioxide is 0.04% of the atmosphere. Just this tiny amount of carbon dioxide can have this huge effect on the warming of the planet. Here's an image of some of Tyndall's original equipment. And as you can see, this is pretty simple stuff. You could probably build this in your basement. And certainly some of these basic experiments can be done by anybody in their own kitchen. I want to emphasize that what we're talking about is radiation. Now, this is not electromagnetic radiation, so it's not the it is electromagnetic radiation. It's not nuclear radiation. So it's not the radiation that you get from a nuclear explosion or from a nuclear power plant. By electromagnetic radiation, we're talking about the radiation that comes from, for instance, this lamp right here. This is a halogen lamp. It's hot to the touch. The radiation produces this light energy, which also has an infrared aspect to it, and that's the heat that comes from this lamp. It's radiating to my hands, and that radiation actually lessens. It becomes less bright the farther away I go. So the radiation then that's coming off the Earth is spreading throughout space and would dissipate in space if it weren't for the role of carbon dioxide and water vapor in our atmosphere, trapping the radiation, making it bounce around and not go straight out into space, and so thereby keeping the planet warm. So nuclear radiation is particle radiation and different kinds of things like X-rays and such. We have also different ways of transferring energy, conduction or convection. And I want you to understand, and I hope this is a review, the different aspects of how the heat transfers. So conduction is when I touch the top of this lamp and it's hot. That's directly conducting the heat from now the cover of this lamp to my fingertips. Convection is the fact if I hold my hand over here, I can feel the warm air as the cold air actually goes around the lamp and then rises above. There's a movement of air. This is the convection. This is important for the development of thunderstorms, for example, in weather. That movement of the warm air from the surface up into the atmosphere and moving around, that convection is not the same thing as electromagnetic radiation. So the electromagnetic radiation is trapped by the atmosphere. Convection is trapped by gravity, right? Those molecules that get warmed up and move up eventually fall back down to Earth through that process of gravity, not because they're trapped by some physical property of the carbon dioxide molecule. And likewise, it's not convection that transmits the heat of the Earth into the atmosphere, because or into space, because there's nothing in space that's touching the Earth, and so it can't be transmitted in that way. So this word greenhouse, then, a scientist would tell you that's problematic, because a greenhouse warms because it also traps convection energy as well as trapping radiation energy. In other words, if you imagine a greenhouse and you have the sun pouring in, that sun is warming up the dirt inside the greenhouse, and then that warm air over the top of that dirt gets trapped by the panes of glass. That's trapping its convection energy. But the greenhouse effect of the glass also traps the radiative energy, electromagnetic radiation, that infrared energy that's coming off of the warm Earth. So it's like a greenhouse, but a greenhouse really is fundamentally different. The point here is that for the planet Earth, the greenhouse is essential. We know that without our atmosphere, the average temperature on Earth would be 0 degrees Fahrenheit, really cold, not the average of 59 degrees that we have today. So let's understand then these feedback mechanisms that also play a role, a very significant role in understanding climate change. If it were just the chemical aspect of the air, this we would know and be able to quantify and have no question about what our future would be. But things get complicated because the warming of the atmosphere interacts with all kinds of other systems on Earth. And one of the most obvious ones of these is the system of the ice sheets over on our poles. So as you know, in the Arctic, the ice sits on top of the Arctic Ocean and also on top of Greenland. But the ice that you see here depicted is that ice that rises and falls with the seasons. Here's an example of what the ice sheet looked like at the beginning of September back in 2018. And this is very typical for what things have been looking like in that period. And what you can see here is that the average ice sheet should have been much larger than it actually was in 2018. Now, as this Arctic ice recedes, it reveals underneath it dark water. Of course, that ice is floating on the water, and so its melting does not actually add to sea level rise, right? Because the ice is still displacing the water, whether it's in ice or it's in liquid. But the feedback aspect of this is the more water that's there and the less ice, the more that energy from the sun is being absorbed by the Arctic Ocean, as opposed to bouncing back off into space. And it's a feedback, it's a positive feedback loop, right? Because the more warming, the less ice, the more energy is absorbed, which makes for more warming, which makes for less ice. So we have this cycle then that adds to global warming. Water vapor is another example of a feedback mechanism, because the planet is covered almost entirely, right, 3/4 by water. There is a lot of water vapor in our atmosphere. And that water vapor interacts, as you know, in the precipitation cycle, right? The oceans warm, they put water vapor into the atmosphere, convection brings that vapor up into clouds, which then cools off and precipitates down to the earth in rain. So that cycle actually is possible because of the warmth of the atmosphere. Again, if the average temperature on Earth were 0 degrees instead of 59, there wouldn't be water, it would be all frozen in ice, right? So the warmer the atmosphere is, the more water vapor it can hold, and water vapor functions much like CO2 in creating a bigger, thicker blanket around the Earth. So if you look at this graph, you see that water vapor actually is a greater forcing, a greater effect on warming than CO2. But water vapor rises and falls with the temperature. So if the temperature were lower, there'd be less water vapor. Now the estimates are with our higher temperature that we have, just this 1 degree Celsius rise in temperature that we have because of the CO2 we've put in the atmosphere so far. That leads to a 4% increase in water vapor in the atmosphere. Now, with this greater water vapor, we also have more clouds that then can block the sun. But there are also other kinds of aerosols, like, for example, a volcano going off and pumping ash and dust high into the atmosphere. This can actually block the sun and provide us a little bit of cooling, but of course that's a short-term process that will drift out of the atmosphere within a couple of years. Clouds are another tricky part. They're a feedback mechanism, but they don't always perform a positive feedback mechanism. They can be negative as well. So clouds, high clouds can actually increase warming, whereas low clouds can actually decrease warming or provide some cooling effect. How clouds shift with the greater warming that we're seeing, this is a real unknown in terms of climate change, and where a lot of the science is happening right now. So that's the end of this lecture for today. I hope that this is a helpful summary for you to go back and look at the Richard Alley book, look at the different presentations from Richard Alley and from others that are available for you, and make sure that you understand this basic science of climate change.